Now let's look at vectors in 3D. So when we are considering our standard basis vectors I, j, and k in three-dimensional space, we can see that we are looking at now ordered triples that are going to be the terminal points of our vectors. So any vector in 3D is going to consist of an x-coordinate, a y-coordinate, and a z-coordinate that is the ordered triple at which our vector would terminate if the vector was initiating from the origin. We can and will refer to this three-dimensional coordinate system as R3. Basically, R3 is the symbol that we use for three-dimensional space. Okay, so now we're going to graph our standard basis vectors, and we'll start off with the I vector. Now remember, I is a unit vector in the positive x direction, and as we just mentioned, any vector, let's say vector v, is going to consist of an x value, a y value, a z value that would be the ordered triple at which my vector terminates if it were centered at the origin, or if the initial point was at the origin. So we're essentially, for the I vector, going to go 1 unit in the direction of x, 0 units in the direction of y, and 0 units in the direction of z. That's going to land at the ordered pair 1, 0, 0. Again, soft brackets when we're talking about a ordered triple or a point, and pointy brackets are representing the vector itself. So this is the I vector with the vector hat on top of it. The j vector is going to be a vector that, if we were to initiate at the origin, it would go 0 units in the direction of x, 1 unit in the direction of y, and 0 units in the direction of z to terminate at the ordered triple 0, 1, 0, soft brackets here because I'm talking about a point. And this is the j vector. The j vector, the entire vector itself, would be represented by j with a hat or pointy brackets talking about the vector itself, not just the terminating point. The k vector will go with a different color here. So my k vector is going to be centered. If we started at the origin, it would have a terminal point that is going to land at 0 in the direction of x, 0 in the direction of y, and 1 in the direction of z. So 0, 0, 1 is the terminal point of the k vector if that vector were starting at the origin. And these are our basis unit vectors in three-dimensional space, and we'll be using these quite a bit throughout the term. So we can think about these new vectors, these three-dimensional vectors, as being scalar multiples of those I, j, k vectors added together. So let's take a look at vector w to start with, and we're going to graph it in three-dimensional space. So we're graphing it in R3. The first thing that let's do is we could also translate this into pointy bracket notation, or look at it as a position vector, where we've got 4 units in the direction of x, minus 3 in the direction of y, and then 2 in the direction of z. And we know that if we were to start vector w at the origin, this would represent the ordered triple at which my vector terminates. We could also look at vector w as being created by adding 3 vectors together, one of which would be a scalar multiple of I, a scalar multiple of j, and a scalar multiple of k. So let's look at these 3 vectors individually and think about what their sum would be. So for I, let's start off with that one, is in the direction of our I vector, but it's a scalar multiple of I, so it's going to stretch that I vector out by a scalar quantity of 4. So 4i is in the direction of I, but with a magnitude of 4. Now we'll look at taking this 4i and adding, actually I need a hat there, adding negative 3j to it. So j itself would be coming off in the positive x direction. However, negative 3j is going to flip that around to go in the opposite direction of the j vector, and also stretch it out by a magnitude, or by a factor of 3. So our negative 3j vector has a magnitude of 3. And then let's also consider the plus 2k vector. 2k is going to, k is in the direction of positive z, 2k stretches it out to a magnitude of 2, right? So here is my 2k vector. And we're going to be adding these three vectors together. So when we add these three vectors together, we're going to create a box, and the sum of the three vectors is going to cross the diagonal of that box. So here we go. We're going to create a floor out of our I and j vectors, or the vectors in the direction of x and y. So let's come parallel to our x-axis here, out 4 units essentially, and then parallel to our y-axis, that's going to be the same length as our negative 3j vector, and then we'll also come up here from this rear corner, or from this outermost corner. And if we want to go ahead and complete the entire box, let's go ahead and do that so we can see here. So we have a pretty good representation of the box here, and the resultant vector, w is the result of adding these three vectors together, is going to start at the initial point of all three vectors, and then we're going to come across the diagonal over here to the other far corner, to the corner that's opposite of it, and we'll say that the sum of these three vectors is going to be this w vector that crosses the center of the box and lands at the far corner on the opposite side. And this ordered triple would be 4 in the direction of x, negative 3 in the direction of y, and 2 in the direction of k. We're going to soft bracket that because now we're just talking about the point. The vector itself would be represented with pointy brackets. Remember, soft brackets for the ordered triple, pointy brackets for the vector. Now let's look at part B here, find 3v, or a scalar multiple of our v vector algebraically. And here's where we're kind of thankful that we've got these algebraic methods, because as you can see, sometimes graphing in three-dimensional space can be tricky. The first thing that I want to bring your attention to, or remind you of, is that we can use pointy bracket notation here and just call that 2, 3, negative 2. These two notations for the vector v can be used interchangeably. It doesn't matter which one you use. I find that I will oftentimes default to pointy bracket notation because it seems a little bit cleaner, a little less cluttered. So the 3v, algebraically, what we'll be doing is simply taking that 3 and multiplying it by the vector 2, 3, negative 2. And just like in two-dimensional vectors, all we really need to do here is distribute this 3 into the pointy bracket. So 3v, or a vector whose magnitude is 3 times as long as v but in the same direction, would be 6, 9, and negative 6, close bracket. So there's our 3v vector, and way easier to just find that algebraically than to try to graph it. And then we want to find the resultant of 2v minus 3w. Let's remind ourselves that the v vector and the w vector from above are 2, 3, negative 2, and w is 4, negative 3, 2. And again, I'm switching over to pointy bracket notation so that it feels a little bit cleaner. The first thing that we need to do is figure out what vector 2v is. So a magnitude that is twice as long as vector v but in the same direction as v, simply take the 2 and multiply it by the components of my v vector. So 2v is going to be 4, 6, negative 4. And same with 3w. As a matter of fact, let's go negative 3w like this, and that's going to be negative 3 times my w vector, which is 4, negative 3, 2. And the negative 3w vector then becomes pointy bracket negative 12. Again, we're just distributing this negative 3 into the parens here. Negative 12, positive 9, and negative 6, close pointy brackets. So now if we're looking for 2v minus 3w, which can also be interpreted as 2v plus negative 3w, we're basically just adding these two vectors together, which is going to be 2v was 4, 6, negative 4, and negative 3w turned out to be negative 12, 9, negative 6. So our vector 2v minus 3w ends up being, we are going to, for vector subtraction, this is going to work exactly like it did in two-dimensional space. We'll say take the x components and add those two together. So we'll say 4 plus negative 12 is negative 8. Take the y components and add those two together. So 6 plus 9 is going to be 15. Take the z components and add those together. So negative 4 plus negative 6 is negative 10. And here is what we would consider to be the resultant of our combination of these two vectors. The last part of this example is to find the magnitude, and just a quick recall that in two dimensions, or actually let's say in two-dimensional space, a vector is going to be given by an x-coordinate and a y-coordinate. These are the components of my vector v. They're also the terminal point of the vector if it was graphed in as a position vector with the initial point at the origin. The magnitude of v, which can be with one vertical bar or two vertical bars, would be the square root of those components squared and added together. That's how it works in two-dimensional space. Well, similarly in three-dimensional space, what we're going to see here is that we would have a vector whose components are going to be an ordered triple, and the magnitude of that vector is thankfully going to be the same, where we just square the components and add them together. So this is going to be the formula that we're using to come up with our magnitude of the v vector that we were given above. And the v vector given above, again, was 2, 3, negative 2. So to find the magnitude of v, which again can be one vertical bar or two vertical bars, both mean the magnitude of v, we'll just take the components, square each of them, and add them together. So like this. So now mag v, I'm switching over to single vertical bars just to demonstrate that you can do that. And we'll have now 4 plus 9 plus 4, and mag v is going to end up being 8 plus 9 is 17, and that will be our magnitude, or the length of the v vector.